you had Fe2 plus ions in here, and you added the KMnO4 to it, okay? And then, again, this was not a color change, okay? Did you stop it when it turned magenta? Yes, but it wasn't a shift from being acidic to basic. All this was that as long as there were Fe2 plus ions to react with it, the MnO4 faded out. So what happened is that you reached a point where all the Fe2 plus had been used up, then it just remained purple because the MnO4 had a distinctive color. So that's one of the unique situations we can do this because the MnO4 has such a distinctive color. We couldn't do this with like sodium hydroxide and hydrochloric acid because everything looks like water. Okay, so that's why we had to have the phenolphthalein when we did the acid base one, because there was not a visual indicator on it. Because if you added too much base, it would still look like water. Okay, so that's the cool thing about the MnO4 is that it provides that color. Then it's just because it's there and that's what's in excess because you used up all the Fe2 plus. So on part one, question number one, you're going to write the balanced equation on the front of that, on page one. If all goes well, you should end up with 4 waters on that balanced equation. Okay? So if all goes well, you should have 4 waters as a product. Question number 3, that's simple. You want to know how many moles of Fe2 plus ions can be oxidized by 0.043 moles of MnO4. That's just a stoich problem. Okay? All that is just a simple stoich conversion. You know how many moles of that? You know the ratio of moles of MnO4 to moles of Fe2 plus. It is a simple stoich thing. 4 is a little bit more complicated because you know the molarity of the MnO4 is about 0.02. Notice that says, it's about 0.02. So this is going to give you an idea of roughly how much of the MnO4 you're going to need. So that again is a stoich problem. You know the volume of your Fe2 plus, you know the mole ratio between the Fe2 plus and the MnO4, and then you know the molarity. So that answer on question number 4 in milliliters should be around 10. Okay? And that's about on the data that you guys had yesterday. For those of you that finished the titration, it took you about 10 milliliters. Okay? It was ballpark, but you got close to that. Now, here's what you're going to do today. Now, you're going to try and find the molarity of oxalic acid. So down there on part 2, I've given you the formula for oxalic acid. Strong acid, weak acid. It's a weak acid, okay? Never heard of it, okay? It's very much a weak acid. So I've given you in here the half reaction for the oxidation of oxalic acid because it's not on any of your sheets, okay? So I've given you the oxidation. Now, you're going to be adding MnO4 to it. So what's the MnO4 going to do? Be reduced or oxidized? Reduced. Yeah, that's going to be reduced because the oxalic acid is going to be oxidized, so your MnO4 is going to be reduced. So on question number 5, you've got the 2, you got to figure out the 2 half reactions, balance those out. So if all goes well on that balanced equation on question number 5, you should have 2 waters as a reactant. Okay? So if all goes well, when you combine, you're going to have waters on both sides of the 2 half reactions. When you balance out the waters, you should end up with 2 waters, dos el aguas, if you want to get Spanish. So you should have 2 waters as a reactant, okay, when that all gets balanced out. So here's what's going to happen in terms of the analysis, okay? So trials 1, 2, and 3, you do not have to show me the entire calculation for all 3 trials, but I want to see 1 complete stoich where you end up with the volume of, you know your volume of your Fe2 plus, you know the molarity of your Fe2 plus. You're trying to find the molarity of your MnO4. Okay? Now, let's talk about this. What two things do you need to find molarity? Moles and liters. Okay? Because moles per liter, right? Pretty simple concept. So, you're going to start with your volume of your Fe2 plus. You know the molarity of your Fe2 plus. Then you're going to do the stoich to find the moles and change that from moles of Fe2 plus into moles of MnO4. Then, if you want to, you could stop there and you're going to say, okay, hey, here's how many moles of MnO4 I have coming out of that stoich. Then you divide that by the volume of MnO4 that it took to reach that point. Okay? So let's say your volume was 9.40 milliliters. Let's just say. So when you look up above volume of MnO4 added, let's say that was 9.40. So then change that into milliliters, or from milliliters into liters, and you're going to get some number of liters here, and you can do that as a separate calculation. Your other option, depending upon how you want to do your stoich, is that you do it as just one big stoich problem. And then your last cell out here is to divide by however many milliliters of MnO4 you have. So if you want to do it all as one big stoich, and then that last cell divide by your volume of your MnO4, that's cool. If you just want to say, hey, here's how many moles of MnO4 I have out of my stoich, and then divide that by the volume of your MnO4, I don't care. It's whatever you feel comfortable with, okay? But this is a lab write-up, okay? Again, 1/5 is not stoich, okay? 1/5 means nothing. It means, congratulations, you can write 1/5. Doesn't mean anything, okay? So, you're going to find the average of those three. So, up there where it says data table 2, okay, where it has molarity of your MnO4, okay, so if you look up above data table 2, that's where you're going to put the average value that you got for your MnO4, okay, so you're going to, that now becomes your known value. So the whole purpose of the first 3 titrations was to find the molarity of the MnO4, knowing the molarity of the Fe2 plus. The next part, now you're going to know the molarity of the MnO4, because that's what you just found, and then you're going to use that to find the molarity of your oxalic acid. So again, on this one, you're only going to do 2 trials on this one. Again, I don't need to see the whole kit and caboodle. I just need to see one complete calculation of that titration. Okay. And then the whole thing that you're searching for is underneath that data table where it says the molarity of the oxalic acid. That's going to be the average of those 2 trials. Okay. Now, let's talk about what has to happen. So, if you look on part 2 in the instructions, this is kind of important that you get this right. So, you're going to start, you're just obtaining 60 milliliters, and then from that, this is where you can use that volumetric pipette, that 25 milliliter volumetric pipette with the bulb. So, because you know you need 25 milliliters of this stuff. So you could use that volumetric pipette on that one, or you could just graduate, so whatever works for you. But again, you're going to put that in. You're going to add 10 milliliters of the sulfuric acid. Okay? Now, you need to add, and these are in little dropper bottles up there on the table, this 1 molar MnSO4. So what it does is act as a catalyst. So we'll talk about catalysts later. So what a catalyst does is imagine that you're dealing with some second graders, God forbid. Okay? and you need to have Timmy and his compadres jump over a bar. Okay, you have to have like a certain bar that they have to jump over. A lot of chemical reactions have what we call activation energy. It's how much energy that you have to put into it. So you can think of it as like a roller coaster. So your activation energy is how high is the first hill of the roller coaster. Okay. Some reactions are very, very low. All you have to do is just mix them together. Okay. Other ones, you like hydrogen and oxygen, that requires some energy to get that reaction started. So that kind of has a hill. Okay. So what the catalyst does is that it lowers the hill. Okay. So you don't have to push it up as high. If you're talking about second graders, it lowers the bar that the kids have to jump over. Okay? So the Mn2, this manganese sulfate is not part of the reaction. Listen to me. Catalysts are not part of the reaction. They're there, they facilitate the reaction, but they're not part of the reaction. Okay? All they do is lower the activation energy. They lower the hill, they lower the bar. Okay? But they're not involved in the reaction. So there's two things that you need to do. You need to add, you take this oxalic acid, you're going to add the sulfuric acid to it, 10 or 5 drops of the MnSO4. Now, then you have to get out a hot plate and you need to heat that up. So you're going to have 2 different beakers. Okay, I would mix them both up at the same time. You need to measure those temperatures. It says to warm it up to about 85 degrees. Watch this so it does not boil. Okay, so LabQuest or temperature or thermometers will be over there. It doesn't have to hit exact 85, it just has to kind of get close to that. The reason that we warm it up is so the reaction takes place faster. You can do it at room temperature, but it would take a really, 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 really long time. So there's 2 things that we do to make this reaction go faster. We heat it up, and we add a catalyst. So in terms of second graders, imagine this. Kids have to jump over a bar, and everyone has to jump over the bar before we can go back inside. So imagine this. It's really cold outside, and you have a high bar, okay? It's going to take these kids forever to jump over that bar. So basically what we're going to do is that we're going to warm it up. We're going to make it like 80 degrees where everybody's bouncing around off the walls, and then we're going to lower the bar, okay? So the combination of warming it up and lowering the bar makes the reaction take place faster. Okay, so that's all we're doing is that we're trying to facilitate a faster reaction. So, okay, I'm done. Let's go do science. Now, let me hold on. Wait. Another thing. Let me talk about another thing. So this sheet that I gave you, okay, so this is basically related to what we've done, but yet it's also an acid-base problem. The only part that you're actually going to answer on this sheet, you treat this as like an assignment. The only thing that you're going to actually answer on here is part B, where it says, draw the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. So if you need to add anything to this, this is what you're going to add here. Everything else you do on another sheet of paper, not on this. The only thing you answer here is that diagram. Everything else on another sheet of paper. Okay, go, be free.